All right, hello. So what I'm going to do in this screencast is walk through equilibrating my system for our first set of free energy calculations, which will be for lidocaine in ethanol, acetone, ethyl acetate, and water. And so how we're going to proceed is I have solvent boxes which have been previously equilibrated for those pure solvents. We'll use some Gromacs tools to solvate a lidocaine molecule in all those solvents. And then we'll get our system to equilibrate for the case of a single solute in solution. And then once that's ready, we'll be able to set up and run our solvation free energy calculations. So we'll go through this activity together in the workshop, but the purpose of recording the screencast is, for you to have a reference, outside of class, and then also if you have any difficulties following along and want to try again later. Okay, so I've already logged on to OSC On Demand, and I'm just going to open up my Pitzer shell. Okay, and my command window pops up. So when I first log into the Pitzer cluster, I'm placed in my home directory. Okay, so in my home directory, I have 500 gigabytes of backed up storage space. When we run our jobs, though, we're going to run from our Scratch space. And so basically, Scratch space is non-backed up, and so it's a faster read-write time. So when we perform our simulations, we'll perform them on Scratch. Scratch is also nice because we can all create a folder right in that same directory and look and be able to help out each other. And so just for the purpose of this activity, I'm going to open up a second shell. Okay, so I have two shells open. This way I'll be able to go back and forth in terms of looking at particular folders. Okay, and so when I log in and I connect to my home directory, I have lots of material in there that I've accumulated over the years. Okay, and so how I just displayed it is the command ls, in case you're not familiar with playing around with Linux. And what I'm going to open up is, so I'm going to cd my force fields directory. And if I look in there, I have a directory called Gromacs traps ff. Okay, and so the force fields we're going to be playing around with for this workshop are going to be the trap united atom force fields. So they're a good set of models, but they're also united atoms models which will make our calculations proceed faster. So given our short time together, it'll help us generate results and be able to work with some data. But everything we do, you can generalize to any model you want. And if you want to have discussions after the class, we could even talk about, say, working with Amber Gaff and generating force fields for anything you can imagine. Okay, so I'm going to leave this shell open in this folder because we'll come back to it and look at it again. And this other shell, okay, so remember I start my home directory. I'm going to move to our Scratch space. Okay, and so the way OSC is set up is you have what's called a project. Okay, and so OSC is a supercomputer which is shared amongst all academics in the state of Ohio, and so you have to apply for resources. So for our workshop, I applied for resource allocation for us to be able to perform all our calculations on. So we were granted 10,000 resource units, which correspond to 100 CPU hours, and we were assigned the project name PMIU 0170. So PMIU is supposed to stand for project, MIU is abbreviation for Miami University. So I'm going to navigate to the Scratch space that's been assigned for our project, or you can think of it as our group. So CD, change directory. Okay, I'm going to go /fs, /scratch, and then our group name is PMIU 0170. All right, remember you can use the tab to complete the command. Okay, if I type ls, right now there's just a lidocaine example directory in there. I'll begin to make more shortly. Okay, and so this is going to be our first set of simulations we'll run. And so what I would say to do, okay, is let's make a directory for each and every one of us to collect all the calculations that we'll run. Right? And so I'm going to do mkdir. I'm going to make a directory, and I'm just going to name it after my username. So back when I first created my account, we were given these very generic usernames. So I am MIU, Miami University, 0105. When you created your accounts, yeah, you have the freedom now to create whatever you want. Okay, but I'm going to create mine after my username. Okay, and then I'm going to copy this lidocaine directory. Okay, this lidocaine example. So to copy the directory, the command is cp-r, lidocaine example, and I want to put it in my folder that I just created for myself, in my MIU0105. Okay, and I just want to call it lidocaine. Okay, I'm going to get rid of the example part. Okay, so now if I open up my MIU0105 directory, okay, and see what's in there, now I have lidocaine. Okay, great. So I'm going to clear my screen before I get going. Okay, and now I'm going to open up lidocaine. Okay, if I type ls to display what's in that lidocaine folder, I have 4 directories, one for acetone, one for diethyl ether, one for ethanol, and one for water. Okay, and so these are going to be the 4 solvents that will put a lidocaine molecule in to perform a solvation free energy calculation. Okay, and so this is the exercise that we'll perform day 1, and then we'll talk about how to interpret the results and things of that nature, hopefully tomorrow. Okay, but goal for today is just to get these systems equilibrated so we can ultimately run our free energy calculations tomorrow. Okay, so let's start by setting up acetone. Okay, so I've tried to fairly automate the process, but no, it's not completely automated because, especially as a beginner, I want you to kind of go through all the input files to a limited extent to at least see what's going on. But in my own research lab, we have some routines to make these things fairly automated when we do large batches of calculations. But again, for now, at least in this workshop, I at least want you to go through the files and look at some things so we can try and talk about what's going on. Okay. Hopefully you don't get sick of me though by the end. Okay. So if I open up acetone and type ls, okay, there's 2 or 3 directories. One's going to be just generated an initial configuration. Then once we have our initial configuration, we'll be able to run an equilibration run with our single solute in that solvent. And then once that's done, we'll ultimately perform our free energy calculations. Okay, so I'm just going to open up initial config, and there's a script in here called gbox solute. Okay, so I'm going to vim gbox solute so I can look at what's going on. Okay, so the first thing that happens, okay, and I should add here, lines begin with hashtags, so those are comment lines. Okay, so the first thing that the script does is it loads the Gromacs module, in case it's not loaded already. If it already is, you can comment it out. And then, okay, the first thing it's going to do is it's going to copy the structure of our solute back from my home directory. Okay, and so if I look at the path, okay, this is my home directory. PMIU0124 is the project that my account was first created for. So it's in that force fields directory, Gromacs trap, where I'm sitting on the other terminal. And then within this molecule XYZ PDB. Okay, so if I were to open up molecule XYZ PDB, these are nothing more than essentially XYZ structures of solutes. Okay, and so I have a series of solutes here. It's easy enough to create one. You can use a program like Avogadro, or if you just go to PubChem, you could download PDB files. So they're fairly easy. The only trick just comes to be that if you need a force field eventually for it, to making sure that the atom number in your XYZ matches up with the order in your force field file. Okay, but it's not something we'll necessarily get into or worry about in the workshop. Okay? But if I were to vim lidocaine PDB, right, it's just a generic PDB file for that molecule. Okay, there's XYZs and PDBs there. So in previous versions of Gromacs, you were allowed to use XYZ files. They're no longer supported, and so I just use OpenBabel to convert them to PDBs. Okay. So if I go back to my script, we load Gromacs. We're going to copy over our lidocaine PDB file, and I'm just going to call it a generic solute PDB. Okay, and so you have a comment here that if you were to say use this as a template for a different solute, okay, you'd want to update the name of your solute here to copy the correct structure file. Okay. We then use a Gromacs program called editconf, which is going to take our PDB and convert it to .gro, which is Gromacs's structure file. And then the next thing that gets copied over is basically we want to take this single solute molecule and we want to put it in a pure solvent. And so the other thing you'll find over in my force field directory, if I go over, flip back over to the other terminal, okay, is if I open up this directory, Equilibrated Boxes, okay, there's two then subdirectories. One is the systems of equilibrated boxes at 298.15 Kelvin and 1 bar. The other one is some equilibrated boxes for supercritical CO2 simulations. But if I open up 298K, what I have listed here is these are just systems that have equilibrated at 298.15 K and 1 bar, and then their corresponding force field. Right? And so if I just wanted to look at acetone npt.grow, this is just XYZ coordinates and velocities taken from an equilibration run of acetone that I ran previously. And so what we'll do is we'll copy this over, and then Gromacs has some nice tools which can generate an initial structure based on this solvent. It can remove solvent molecules to accommodate your solute, say in that box, and can add more depending on the size of the system we desire. Okay. So I'm going to close out of that, :Q. If I go back to our first shell, so what this is doing is it's just copying over our equilibrated solvent box. And there's a note that if you want to look at a different solvent, you can just update this for that solvent name. And then also know if you want to create a huge library of possible solvents, it's easy enough to equilibrate the new solvent and deposit its GRO file there. Okay, and so then Gromacs has this nice built-in tool, edit conf, and so what's happening here is just like when we convert it from PDB to GRO, it's going to take our solvent GRO file, okay, and it's just going to create a new solvent GRO file in which it's unwrapped molecules, so it's accounting for periodic boundary conditions to make my molecules whole, so that then it can use another tool called solvate to solvate my solute in my solvent box. And then here I'm specifying a cubic box 4.5 nanometers in length. Okay, so 4.5 nanometers or 45 angstroms. And I'm going to call that final output configuration lidocaine input.grow. Okay, so we can talk a little more about box sizes later, but basically, right, we want a system in which our solute's infinitely dilute. So I just want to make sure my box is large enough that remember we're going to be modeling things with periodic boundary conditions, that if I'm my solute looking out with periodic boundary conditions, I'm not going to see myself in that periodic image, right? So I'm going to have enough solutes so that this infinite dilution limit is essentially correct. Okay. Okay, so I'm going to close out of this. For the purpose of these solvents with lidocaine, we're not going to have to update this at all. But if you use it as a template, as you can see, there's very little to update. Right? Just maybe my solute and solvent. Okay, and if you want to change, say, the box size, you can. Okay, so remember this already loads Gromacs for us. Okay, so to run the script, okay, the command is just going to be period / and then the name of the script, gboxsolute.sh. Okay, so if I run it, I get some messages from Gromacs. I get a couple warnings, but no error messages. Right, so life is okay. Okay, so if I type ls, I can now vim lidocaine input.grow, and what I'll see is now I have a box in which the first molecule is going to be lidocaine. Okay, and then I'm going to have, in this case, 743 acetone molecules, which is how many molecules solvate estimated that I would need to get a box of 4.5 nanometers in length. So I'm going to close that, and now I'm going to move over to our NPT equilibration directory. Right? So I'm trying to keep things separate so that if things go wrong, I can try and keep track of where they might be going wrong. Okay. So if I open up that directory and type ls, okay, now I have 4 files. Okay, the first one that's going to be in there, this lidocaine input.mdp, that's going to be our input file that tells Gromacs ultimately how to do the calculation. Okay, so that needs to be there. If I'm looking at a different solute, I can just copy that, and I would just rename it for whatever system I'm looking at. But there's nothing in that file that has anything to do with the molecules I'm actually looking at. All right, so the first two things that we're going to look at are essentially the two things that are going to get this calculation set up are these two scripts named setup1 and setup2.sh. Okay, so if I vim setup1, okay, so what setup1 does, okay, and at the very top there's step-by-step of how essentially this is going to work. Okay, but the first thing it's going to do is it's going to copy from that initial configuration directory our new initial structure of our simulation, lidocaine input.grow. Okay, so I would just update this if the solute name were different. Okay, and then what I'm going to do is from that Equilibrated Boxes directory. Okay, so if I go back here, we were in Equilibrated Boxes before. And if I look at acetone, there's two files for acetone. There's this npt.grow, which was our structure file, and there's acetone ff.top, which is our think of it as a Gromacs force field file. Okay, so it describes how many molecules in our system and what force fields to use to describe our interactions. Okay, so we want to copy this, and then we're just going to update it for our current system. Okay, and so what that'll look like is, okay, I copied my initial structure, then I copy this force field file. Okay. And then once I copy that force field file, I rename it lidocaine, ff.top, and then there's a series of updates that I need to make to that file. Okay, and so I list them all here, and we'll go through it interactively, but you can always refer back to it here. So I start by running setup1. Okay, if I type ls, okay, my input file's there, and now I have a new force field file for this simulation. Okay, I'm going to vim this force field file. Okay, and so if I get in there, I just need to update it. Okay, and so what I mean by update it is I'm going to start down here. So the first thing it does is it loads my trap force field database. Okay, and essentially this just contains all of the interaction parameters used in our trap model. Right, so our building blocks, which we'll do, are used to assemble molecules. And then after that, it loads specific files for the molecules present in my system. Okay, so acetone's already here, right? I just copied it from that Equilibrated Boxes directory. And what I'm going to do is, okay, so I haven't, okay, so let me redo that. So if I undo, okay, so if you're not familiar with Vim, okay, to get into typing mode, I just type I to get into insert. Okay, so if I were to say try and do this interactively, if I were to highlight this, right, there's no right click and copy, but what I can do is I can just press my middle wheel and I can paste. Okay. The other way is we can use verbose mode, which I can show you, or visual mode, which I can show you next time. Okay. So I'm just going to copy and paste that section. Okay. And what I want to do is now, besides already having acetone, now we need to load our force field for lidocaine. So I'm going to load my trap file for lidocaine, okay, for free energy calculations. Okay, so that file is going to be in the same directory here where the trap one is in, this general molecule ITP file. Okay, so I'm going to go to my other terminal. I'm going to take a look at what that looks like. Okay, so I was in Equilibrated Boxes, backing up a directory, backing up two directories. And now I'm going to open up molecule ITP. Okay, so molecule ITP just contains ITP files. Okay, so I have this big trap force field database. Now these described how I take those parameters and assemble them to describe the interactions of a molecule. So now for components that will become solutes and free energy calculations. Okay, so if I were to look at lidocaine, there's going to be two different versions of my ITP file. Okay. So I have one that's lidocaine _ shake, okay, and all the shake part means is if you were to use velocity of relay and use shake to constrain bonds, and when we constrain bonds, we'll constrain hydrogen bonds. The bond that you're constraining, those two atoms need to be in the same group, okay, and that doesn't need to mean anything to you. It's just shake is my note that it's set up properly to work with shake. Now, what's relevant or important for free energy calculations is I have two versions of this. One has this _FE extension. Okay? And basically the only difference is in Gromacs, you name a molecule. Okay, and so this first plain old lidocaine force field file, I just call my lidocaine molecule Lido, L-I-D-O. But what I typically do, or the convention I've adopted, is for components that'll become solutes. I create this, I just essentially copy my original ITP and make it, underscore fe.itp. And all I do is change the name of the molecule to be SOUT, capital SOUT. And then the only purpose for that is when we set up our free energy calculations, you need to name the molecule as being coupled and decoupled. And I just have a generic name of SOUT for the molecule that's going to be coupled or decoupled in my system. And if I just have a single solute and some solvent, it doesn't really matter. I could easily name that solute molecule, but it comes in handy if, say, I'm actually trying to compute solvation free energy of, say, water and water, which we'll see later on we can relate to vapor pressure. Then the S out becomes useful in terms of distinguishing the water molecule that's going to be coupled and decoupled as compared to the regular water molecules. Okay, and so I want to copy this. Okay, so I've got it highlighted, and so I'm going to delete acetone to ITP. I think I have the whole thing highlighted. Okay, I'm going to pass the lidocaine shake FE. Okay, so now I have the proper force field file set up. The next thing I'm going to update is I need to update the number of acetone molecules in my system, and then I also need to tell it that lidocaine is going to be in here. Okay, and so how I do this is when we looked at our initial configuration file, remember lidocaine was the first molecule. Okay, and when I use this FE file, okay, my molecule is called SOUT. Okay, so I'm going to have one SOUT molecule, but now I'm going to need to figure out how many acetone molecules I have. Okay, so to do that, I'm going to actually escape, then save and quit, Shift:WQ. Okay, and I'm going to look at my input.grow file. Okay, and I know we looked at it already, but I've already forgotten how many molecules are in the system. Okay, so the first molecule is just lidocaine. Okay, then you see the second molecule becomes an acetone molecule, right? Acetone is just the name that I had assigned to acetone. Okay, lidocaine for now, the PDB, the generic name of PDB assigns as lig. It'll automatically be updated to agree with our force field file, so no worries on that. But to go down the bottom of my file, I'm going to type a double bracket. Okay, so that's, I don't know, with a button next to pipe, I don't know if that actually helps explains things at all. But if I go down to the bottom of my file, I have 744 total molecules. So one of them is lidocaine, so that means I have 743 acetone molecules. Okay, so I'm going to quit out of that, and I'm going to open my force field file back up. And so the total number of acetone molecules I have is 743. Okay, so now I've updated it, so I've added lidocaine, updated the molecule counts. I now load the lidocaine force field, okay, and now I just have a couple of small tweaks. Okay, my couple of small tweaks, okay, is on this line here. Okay, so what these correspond to is this first parameter is just your potential form. Okay, we're using an LJ potential, which is 1. Combining rules, all right, which can be typically it'd just be Lorentz-Berthelot geometric. Would be the two common ones. Gen pairs is in, so these last three correspond to molecules that have 1,4 interactions. Okay, and so typically there's scaling rules for 1,4 interactions. Right, so to complement your dihedrals, 1,4, and then if there's say 1,5, 1,6, 1,7. So 1,4, the interactions are typically scaled. 1,5 and 1,6 are typically full. And so what we'll have to do is when we, in that ITP file for lidocaine, okay, so, all right, so if you have a molecule, I keep trying to use my wheel to scroll down, but it doesn't work, that has such intramolecular interactions, right, you need to explicitly list all of those pairs, right? These are all my 1,4 interactions. Interactions greater than 1,4 will be treated as full. Okay. So what pairs does is if I have a list of 1,4 interactions in my force field file, then what gen pairs will do is it'll generate the corresponding LJ and electrostatic interactions for, well, I guess just the corresponding scaled electrostatics for the 1,4, and then LJ parameters for those. And then what fudge LJ and fudge QQ are is just my Leonard-Jones scaling and charge scaling. Okay, so for the solutes, none of them have. We're not going to be looking at any big molecules that have 1,4. If they do, we'll look at those cases. But this is just unique in that I have these small solutes in which I didn't have 1,4 interactions when I equilibrated the boxes, so I just had it turned off. But when I put a big solute in it, now I need to account for 1,4s. Okay, and so I'm just going to change gen pairs to yes. Fudge LJ, our LJ scaling is going to be 0.5, and QQ is 8,333. Okay, and so we can talk about more what this means later on. But then the last thing to do then is just update our comments. Okay, and I don't think we have any comments really to update. The only one we have to change would be up here. Now we have a box of 1 lidocaine solvated in 743 acetone molecules. Okay, but again, sorry, you've got to do some things manually. We could automate this for the most part, but I think it's good to go through it. Okay, so I'm going to save and quit. Okay, escaped, Shift:"Q. Okay, and yeah, it's okay. So now that guy's all set up. And so if I vim setup 2, okay, all that happens in setup 2 is, well, you need Gromacs loaded. So if Gromacs isn't loaded, you would uncomment this or just load in the command window. We're going to use the Gromacs gromp command to look at the input files that we have and make sure that everything is correct, and then get the final input files set up for our simulation. Okay, and so it's just going to be period / setup 2. Okay, and again, I'm going to point out that our force field files is ff.top. So lidocaine input.grow is just our initial structure. Input.mdb is just our run parameters. That doesn't in there list anything specific to our molecules. It's just the name of the file you would update, say, for an equilibration run. Okay, and we can peek more at that later. And then when I run it, so did I switch cell? So setup 2. Well, so basically it's telling me that it doesn't recognize this gmxd command, which tells me that Gromacs isn't loaded, which is odd because I thought I had loaded it. So if I take module list, okay, I can look at the modules I have loaded, and Gromacs isn't on there. Huh. Again, I could have sworn that I've loaded Gromacs before. Okay, so no worries. I'm going to load Gromacs. I'm going to uncomment that part to load Gromacs. And I'm going to try again. Okay, we're on setup 2. Hey, and bam, life is good. All right. I do get one warning. All right, and so basically my one warning is, like I told you, in the structure file, there's a lig assigned to, in the initial structure, lig was the molecule name assigned to lidocaine, which is default from PDB. And so it's just saying, hey, there's a mismatch, and it updated it to SOT. And then all this is saying is that the names of the sites in my lidocaine force field file differed from what was in the input file, and that's again just because PDB in the conversion only wants a single character for the site, but when I create the force field, I give them more specific names to differentiate them, and they show the matching here. Okay, but that's it. So if I type ls, all right, now everything is set up, and I'm ready to submit my first job to equilibrate my first system. Yeah. Okay. And so before we do, and so how we run this is with this submission script. And so I want to vim this submission script. Okay, I'm going to VIN script submit just so we can look at it. Okay, and so lines that begin with hashtag are again comments. Hashtag PBS, those are commands for the scheduler, right? So we're going to submit our job to run on the supercomputer. The scheduler is the person that tells you when your job can run, essentially. And so I give the job a name. So this job is going to be called lidocaine EQ. You could update that for another solute. And don't worry about this. Okay. When you copy my files, what you need to make sure you update is your email address. Okay. So what will happen is when you submit it, if this email address doesn't match up with the email address in your account, it's not a huge issue, but you'll get an email from OSC, you and me, because I want to make sure that no one's improperly using OSC. Right? I had a student once that submitted a ton of jobs. They forgot to update it. They used my email account, and I even misspelled my name. And I got an email from OSC asking if we were essentially abusing the system. Then this next line, this little m, so what will happen is OSC will send me an email when the job's complete. Then we need to tell it what resources we want. So we're going to run on Pitzer. Pitzer actually has 40 processors per node. So if I want to run on a single node, which is still a serial job, and so, I guess, what I've always just done, stemming back to being an undergrad, is when you span multiple nodes is when the performance of your code really starts to suffer. But if you're on a single node, data connect isn't an issue. 40 nodes, though, would be a lot to scale to for our simulations. So I'm going to request one node with just 10 processors on that node. And then I'm going to estimate a wall clock time of 24 hours. So when you estimate a wall clock time, it can be really hard to generate an estimate initially. So I don't know exactly what this will take. I think it'll take far less than this, right? I'm hoping that this takes, on the order of, an hour, 2 hours. But I'm going to request 24 hours, okay? So kind of the pros and cons of this. If I request a huge wall time, I'm going to be waiting in the queue longer, okay? It's going to take longer for my job to get scheduled to run. But if I underestimate my wall time, what happens is when I hit that wall time, in terms of what wall time I'm requesting, if I hit that time before my job's done, my job gets killed, and that's annoying, especially in a workshop like this when it'd be a pain that if you're hoping to have some results the next day. Okay, so for now I'm just going to estimate 24 hours since I haven't actually tested these out yet on Pitzer. We load Gromacs, right? So even though we had loaded it in our session, basically this is going to run, or the supercomputer is going to run it for us. So then we need to make sure they load Gromacs for us. This is just a command so that they open up the directory that the job was submitted from. And then this is a Gromacs command. So this gmxd and then md run. It's going to run a Gromacs MD simulation. Then we get the flag -def nm. And so all that means is the default name of all my input files is lidocaine_npt. So remember, Grom generated all these files, and they were lidocaine npt with some extension. And so then this will give us output files of the same format. Okay. So I'm just going to, save and quit since I updated my email address. Okay. In this, you would update based on your solute. And then I'm ready to run it. So I run it as qsub script submit. Okay. So my job has properly been counted. Now I just realized that I made a mistake. Okay. So the issue I made is I need to tell it what account I want to bill from. Okay. So I actually have 3 projects, right? And so I just need, basically it's telling me I just need to update that, and then I'm all set, right? And so click qsub script, job submitted, you're home free. Okay. So I'll make sure I add the project name so jobs for me will run, but for all of you, you're only in one project, so you have no problem. Okay, but that's setting up your first job. If I wanted to do the other ones, I could back up 2 directories. Okay, open up say diethyl ether and repeat. Okay, so I won't go through it. In the purpose of this video, it'll become too long. But in class, we'll be able to go through everything together. So if you have any questions, by all means, let me know. If you want to see me go through some more, by all means, let me know.